Today we have a topic, is a pressure sensor. And this time we will use piezo resistance for the sensing mechanism. Piezo resistance, if you look at this formula, this is resistivity. This one is stress. So if we have pressure, means we have stress, we can make the resistivity change. So by measuring the resistance change, then we can get our signal output. So this is the mechanism we will use for piezo-resistive pressure sensor. Okay. Ahwan, what is this one? What is this? What is this one? Amin, what is this one? Okay. And what is this one? We have what to make this one change? Okay. Read this.
Assume that piezoresistive applied is clear, which is true for small strength, but I can go at successful large strength.
Okay, then read this.
Relationship between electric field and current discharge is.
Okay, so I made a mistake. This one is resistivity. This one is electric field. Electric field is this one. This one is resistivity. This one is stress. This one is current density. And this one is the relation between stress and the electric field. So the unit for electric field is volt per meter. Unit for resistivity is ohm meter. The unit for stress is Pascal. The unit for current density is ampere per meter square. Then, in order for these two units can be added together, these two items needs to have the same unit. So if this item unit is ohm meter, for this unit, the unit to be ohm meter. And if this unit is Pascal, the unit for this one must be ohm meter divided by Pascal. So Pascal cancel out. We are left with ohm meter. Ohm meter and ohm meter can be added together. Okay, Kumail's friend, what's your name? Marston. Okay, why the unit for this one is ohm meter divided by Pascal? Why is that?
To get the relation true dimensionically.
Yeah, okay. Then if you go further, ohm meter multiplied by ampere divided by meter square. So meter cancel out. We are left with 1 meter in the denominator. And ohm multiplied by ampere equal to volt. So the dimension got to be compatible. Okay, Ahwan, why ohm meter times ampere per meter square equal to volt per meter?
Divided by M10.
Then?
the A and O can become the B.
Okay, so rho E is the resistivity. We use tensor. You can think tensor as a vector or matrix, because imagine we have x, y, z. We have 3 directions. Then the electric field in x direction, Vx, electric field in y direction, Ey, electric field in z direction, Ez. So this one should be a vector. So if this one is a vector, then this one is also a vector. Current density in x direction, Jx. Current density in y direction, Jy. Current density in z direction, Jz. So if this one is a 3 by 1 vector, this one is a 3 by 1 vector. So this one must be n by 3. So 3 by 1, 3 by 3. 3 by 3 is 3 by 1. The result is 3 by 1. For matrix to be multiplied, they got to be the dimension A, B, B, C. The result is AC dimension. Okay, but here pi is a piezoresistive tensor. Again, matrix. You can take it as a matrix. Piezoresistive. Then for cubic material, like their atom are in the regular pattern, like a cube, we have 8 atoms at the top and 8 atoms at the bottom. So for a cubic material, we can simplify this equation into this one, into 3 equations in one direction, electric field in one direction. We move the resistivity to the left-hand side. The right-hand side can be simplified to this one. J1, J2, J3. This one is shear stress in 1, 2 direction, shear stress in 1, 3 direction. Normal stress in 1, 1 direction, sigma 1, 1. Normal stress in 2, 2 direction. Normal stress in 3, 3 direction. And pi 1, 1, pi 1, 2, pi 1, 4 are piezoresistive coefficients. So let me show you the stress definition here. Go back again. Okay, suppose we have a cubic material and atoms. Okay, now we apply force. Then if this is 1 direction, this is 2 direction, this is 3 direction. The force applied to this surface, the 1, 0, 0 surface, we have a force. Then the force divided by the cross-sectional area. So we have force divided by the area is stress. So the normal force, the force normal to this surface, divided by area of this front surface, we have stress 1, 1. And the normal force in this surface, F2, divided by the surface area, A2, we have normal stress, sigma 2, 2. The same for this surface, we have stress 3, 3. So they are normal stress, NORMAL, normal stress. Okay, repeat after me. Normal stress, Ahwan. Normal stress. So what is the definition of sigma 1, 1?
The force divided by the area.
Then if we have because we have a force applied to this surface, normal force, normal force. But if we have a force parallel to the surface, we apply a shear force. So the force in normal to the surface, we have normal force. The force parallel to the surface. See, if I apply shear force, this is shear force, this is normal force. So shear force divided by area, we get shear stress, shear. So if we have a shear force on this surface, but pointed to the two direction, the shear force, this shear force divided by the area, we get shear stress. We use tau 1, 2. So the first subscript means the normal surface. This is 1 surface, the first subscript. The second subscript is the direction of this shear force. The direction of this shear force is in two directions. So we use this symbol to represent shear stress, tau 1, 2. And 1 is the normal vector direction, 1. 2 is the direction of this force. So what is tau 1, 2? Continue. Tau 1, 2. What is 1? What is 2?
就是往2那边的力。
Okay. Then again we have shear stress tau 1, 3. So come here to draw tau 2, 3. Tau 2, 3. 2, 3. TA, can you draw tau 2, 3? Tau 2, 3. Do you know why tau 2, 3 should be here other than here? What's the difference?
From 2.
Tau 2, 3. Why tau 2, 3 should be on this surface other than here? Why? Did you see any difference? The TA draw tau 2, 3 on this surface and you draw tau 2, 3 here. What's the difference?
The surface on 2.
Shear force should be on the surface. And you draw this force, looks like it's not on this surface. Looks like it's normal to this plane. Then draw tau 2, 1. Tau 2, 1. Let me draw a bigger picture for you. Clean. Okay, a new clean cube. We have one direction and two direction and three direction. Okay, draw tau 2, 1.
This.
Draw. To be precise, this one is off limit. Can you draw tau 2, 1 totally on the surface, not off the surface?
This
TA, can you draw tau 2, 1 totally applied to the surface, not off the surface? To be precise, this part is not on this surface. This part is off the surface. Draw tau 2, 3 again. Tau 2, 3. Okay. Go back, please. 阿环 draw sigma 3, 3. Sigma 3, 3. Okay. Sigma 2, 2. Okay, thank you. Kumel, draw tau 3, 1.
already.
Tau 3, 1. Tau 3, 1.
No?
Tau 3, 1.
Outside.
Tau 3, 1. Okay, stand aside. Okay, bottom, draw tau 3, 1. Okay, right. Tau 3, okay, bottom can go back. Do you know why bottom is correct and yours is wrong? Do you know why?
Yes, it should be here because the surface, if we can.
Tau 3, 1. What is the meaning of 3 for tau 3, 1?
Surface.
And what's the meaning of 1?
Point shear stress.
What is the meaning of 1?
Sorry?
Tau 3, 1. Tau 3, 1. What is the meaning of the 3? What is the meaning of 1 for tau 3, 1? What is the meaning of 3? 3
3 is surface. 3.
and 1.
1 is the force. The shear force which we have.
So 1 means which direction?
It's already
1. Okay, draw
1.
tau 3, 2.
3, 2.
Tau 3, 2. Okay, draw tau 2, 3.
2, 3.
Yeah, tau 2, 3. Draw tau 2, 1.
2, 1.
Okay. All right. Thank you. So this is our first equation for the cubic material. Okay, next page. So first equation, second equation, third equation. Epsilon 1 is the electric field in one direction. Patik, is that your name?
Prakash.
Badak, sorry,
Deepak.
BPAP. Okay, what is the meaning of epsilon 2? Yeah, what is epsilon 2? Again, what is epsilon 3? In which direction? Okay. So, particle, what is epsilon 2?
Electricity.
Huh?
Electricity.
Can you repeat? Epsilon 2. What is epsilon 2? Epsilon 2. Kumel, what is epsilon 2?
It's electric field. Electric field.
In which direction? Okay, so particle. Sorry, again. B-part. What is J3?
Electricity.
Huh?
Electricity.
Ian? Ethan, what is J3? So you are Ian. Leo, what is J3?
Current density.
In which direction? Okay, current density in 3 directions. So you have the 3 equations for which material? Muslim. Which material can we use the 3 equations?
Cubic.
Cubic material. Okay, sit down, please. So Muslim, you don't need to stand up. You just sit and reply. Okay, for cubic material. So silicon is a cubic material. So for silicon, we can use these equations. Next page. And tensor, if we have vector 1, U1, U1 equal to A times U2. 3 by 1 vector. 3 by 1 vector. So this is 3 by 3. So this matrix can convert a vector to another vector. Then we call this tensor. Tensor can convert one vector into another vector. So this is a tensor operation. For example, we have stress sigma 1, 1, sigma 2, 2, sigma 3, 3, and sigma 1, 2, sigma 1, 3, sigma 2, 3, sigma 2, 1, sigma 3, 1, sigma 3, 2, sigma 3, 3. Let's clean again. 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, 2, 3, 2, 1, 3, 1. So R1, this one should be what? 3, 2. Okay. So if we have a cubic material, we have cubic material, we have 1, 2, 3, we have 3 directions. 1, 2, 3. Okay, so we have a direction. Say this is 1, 1, 0, 0 direction. So 1, 0, 0 direction. So this matrix multiplied by this, the result is sigma 1, 1, sigma 2, 1, sigma 3, 1. But remember, sigma 2, 1 equal to sigma 1, 2. Sigma 3, 1 equal to sigma 1, 3. Actually, sigma 1, 2, we use tau 1, 2 for shear stress. So again, tau 1, 2 and sigma 1, 2, we can use sigma to represent shear stress, but sigma 1, 1, sigma 2, 2, sigma 3, 3 are normal stress. Sigma 1, 2, sigma 1, 3, 2, 3, 2, 1, 3, 1, 3, 2. They are shear stress. You can also use tau. But if I can also use sigma. It's just a symbol. So sigma 1, 2 equal to sigma 2, 1. Sigma 1, 3 equal to sigma 3, 1. Sigma 2, 3 equal to sigma 3, 2. For shear stress, we can change the subscript. Their values are the same. So again, is sigma 1, 2 equal to sigma 1, 3? No. Is sigma 2, 3 equal to sigma 3, 2? Okay. So see, for this one, remember sigma 2, 1 equal to sigma 1, 2. Sigma 3, 1 equal to sigma 1, 3. Okay, then you can draw sigma 1, 1. Normal stress and sigma 2, 1 on two surfaces but pointing to the one direction. Sigma 3, 1 on three surfaces but pointing to one direction. So, Amin, could you read the second point?
So she straight tensor T has the direction V as input and produce the stress T of P on the surface normal to this vector for output, thus expressing a relationship between these two vectors.
Okay, remember sigma 1, 1, sigma 2, 1 equal to sigma 1, 2, sigma 3, 1 equal to sigma 1, 3. So we have sigma 1, 1, and this is sigma 1, 2, this is sigma 1, 3. So V is the direction. So 1, 0, 0, this is V. V is the direction 1, 0, 0. And this one is the Koch stress tensor T. So Koch stress tensor multiply this direction vector, we can get the stress on the surface 1. Surface normal to this vector is one surface. So T multiplied by V, we can get sigma 1, 1, sigma 1, 2, sigma 1, 3. So these are the three stress. Sigma 1, 1, sigma 1, 2, sigma 1, 3. The stress applied to the surface 1. And for this surface, the normal vector of this surface is 1, 0, 0. So this is Koch stress tensor. So tensor can apply to a vector. We can get a vector. Okay. Ian, Leo, could you read the first point?
Geometric objects that describe the linear relations between vectors, scalars, and other tensors.
Okay. So you can think tensor is a linear relation between two vectors. This is a vector. This is a vector. The relation between two vectors is a tensor. 张量 tensor, Chinese terminology. Okay, so Martin, what is tensor?
It's the relation between vector and scalar.
Okay,
R2.
okay, fine. Thank you. Next page. Yeah, I just described this. I explained this, the normal stress and shear stress definitions. And T1, T2, T3, the direction vector. So this is Koch stress tensor. So it's a name is good for you to remember, because for mechanics, usually stress is the basic concept for mechanics. I just read a paper. It's about electrostatic motor, and the paper is written by electrical engineering professors. Okay, in the paper, they have some mechanics relation, because for motor, we have beam to connect the electrostatic port to the shuttle, the motion port. So they need to have an equation to describe the input to the output, but it's mechanics. It's not voltage or current. So I read the paper. So all the mechanical equations are wrong. So, but we cannot blame electrical engineers, because they do not understand those basic concepts of those mechanical engineering stuff. But for some mechanical engineers in this room, I hope after I teach them, after they learn some basic mechanics, they won't be too unfamiliar with all these concepts. Okay, next page. Remember we said the cubic crystal. For silicon, yeah, we can use this simple model to show the silicon crystal. We have 4 atoms at the edge. We have 1 atom at the center. So this surface, because the normal vector to this surface is 1, 0, 0. So we call this surface 1, 0, 0 surface. And this direction is 1, 0, 0 direction. It's a vector. 0, 1, 0 vector direction. 0, 0, 1 vector. So this one is direction, direction, direction. And this 1, 0, 0, left parentheses, right parentheses represents the surface. QML, why do we call this surface 1, 1, 0 surface?
Yes.
Why is this surface 1, 1, 0 surface?
It's for second, this one.
Why? Why we give the name of this surface 1, 1, 0 surface? We use normal vector of the surface to represent the surface. Okay, Leo, why do we call this surface 1, 1, 0 surface? Because what? 1, 1, 0 surface. Why do we call this surface 1, 1, 0 surface?
Because 它还有 x 的方向和 y 的方向。
Remember, we use the surface normal to represent the surface. Leo, why do we call this surface 1, 1, 0 surface? Sorry, your name again.
Bebop.
BPAP. B-E-E.
B-A-P-A-R-K.
B-A.
B-A-R-K.
B-A-R.
Yeah.
Bar.
B-A-P-E-A-R-K.
B-A-P-E-A-R-K.
Yes, Bebop.
B-A-P-E-A-R-K.
Yeah.
BPAP. BPAP, why this one is 110 or 110 surface? Bottom, why this surface is 11?
Because the X have 1 and Fy have 1, then 0 is nothing, so it's 1 or surface.
The surface normal of this one. So the normal vector is the normal vector to this surface is this one. For this one, the vector is 1, 1, 0. So the vector normal to this surface is this vector, and this vector is 1, 1, 0 vector. This direction is 1, 1, 0 direction. And because this is the normal vector to this surface, normal means perpendicular, vertical. This vector is perpendicular to this surface. So this vector is the normal vector of this surface. So we use the normal vector to represent the surface. So that's the reason we call this surface 110 surface. So Ian? Ethan. So why is this surface 110 surface?
Normal vector. The surface
Is what?
is 110.
Okay, good. And Kumel, why do we call this surface 111 surface? Again, why do we call this surface 111 surface?
Because the normal surface is 111.
The normal vector.
Normal vector.
Look at this surface. The vector normal to this surface is from this atom to this atom. So we can draw the vector from this atom to this atom. For this vector, the three components is 1, 1, 1. So that's why this surface is 111 surface. And for wafer, when we fabricate, the wafer foundry, they make a wafer. The wafer looks like this. Cylinder. So this one is a wafer, silicon. Not silicon wafer. The raw material of wafer. So we can cut this cylinder slices to create wafer, silicon wafer. You can cut it this way. You can cut the other way. There are many ways to cut the cylinder. But if the surface is 110 surface, if you cut the wafer, so this is 110 surface, then you create 100 wafer. If the top surface, the atom surface is 111 surface, so you cut the wafer this way, you create 111 wafer. So wafer, we use the surface normal to define the wafer type. So we had 100 wafer, we had 111 wafer, we had 110 wafer. Kumel, what is 100 wafer?
This one is the first surface, which is and this is also 0 and this one is also 0. So that the first one is 1. That's why we have.
How many kinds of wafer do we have?
3.
3. What are those 3 kinds?
1, 1, 0, 0, 0, 1, 0, 0, 0, 1.
Again, can you give me the 3 types of the wafer?
Yeah.
Again, your answer.
0, 0, 0,
And
0, 1, 0.
In this second world, 1 0 0, 0 1 0, 0 0 1,
Yeah.
they are the same. There's no difference. If you turn this cubic 90 degrees, the axis, you rotate this cube minus 90 degrees, then 0 1 0 becomes 1 0 0. So 1 0 0, 0 1 0 0, 0 0 1. These 3 surfaces are the same. For a cubic material, you can rotate, you can throw it, and there's only 3 surfaces: 1 0 0, 0 1 1 0, 1 1 1. For all other surfaces, for this surface, we say 1 1 1. For the surface passing this point, and this point, it could be -1, -1, 1, -1, -1, 1. But for this surface, -1, -1, 1, and this surface 1 1 1. Actually, they are the same. They are equivalent. So 1 1 1 is equal to -1 -1 1, equal to -1 1 -1, equal to -1 -1 -1, equal to 1 -1 1. They are the same. They are in a family, 1 1 1 family. And 1 0 0 family, we have -1 0 0, 0 1 0, 0 -1 0. And 1 1 0 family, we have -1 -1 0, 0 -1 1, 0 1. So they are the same. So there are only 3 atom surfaces. Okay, next page. Then we need this for our other slides after this one. Direction cosines. Okay, so in this coordinate system, we have 1 1 0 direction, we have 0 1 1 direction, we have 1 0 1 direction, because this is 1 0 0 direction, this is 0 1 0 direction, this 0 0 1 direction. Okay, so these are direction vectors. And this is, okay, the same x, y, z plane. So we have a vector from O to A. Then the component is A, B, C. So for this vector, the angle between this vector and x coordinate, we have angle alpha. For this vector, between this vector and y axis, we have angle beta. For this vector, between this vector and the z axis, we have angle gamma. So the direction cosines are cosine alpha, cosine beta, and cosine gamma. The 3 direction cosines for vector OA, for vector ABC. Okay, so get a paper. And write down your name and your student ID. And draw this figure and draw the 3 triangles. The 3 triangles, you can use the 3 triangles to prove cosine alpha equal to this value, cosine beta equal to this value, cosine gamma equal to this value. So draw this figure and draw 3 triangles. And use these 3 triangles, you can prove the 3-dimensional cosines can be written in these 3 expressions. Camera off. Sound. Good. Next page, please. Now we have an example. The resistor longitudinal direction is 1, 1, 0. Then the wafer we use is 1, 0, 0 wafer. Then so 1, 1, 0 direction pi L, 1, 1, 0 direction pi T. Please use the 3 equations. Okay, previous page. Please use these two equations to calculate. Next page. The values here. Okay, everyone, get your paper. Remember to find out L1, M1, N1, L2, M2, N2. Then you can get the equation. Camera off. And test volume, okay. Now we have an example. Okay, we have a pressure sensor. So this pressure sensor, we have a diaphragm, we have a cavity. Then this is a MEMS, and here we have anchor. So fix here, and this is side view. This is top view. We look at from the top. We look at from the side. So from the top, in the longitudinal direction, because this is longitudinal direction. Bipa, what are you doing? Are you checking my YouTube video? If not, put it aside. If you look at the top, we have piezoresistor, polysilicon piezoresistor here. And another piezoresistor, polysilicon in a transverse direction. So we have 2 piezoresistors. Then the 2 resistors orientation are 1, 1, 0 direction. So this is 1, 1, 0 direction. This one is also 1, 1, 0 direction. Muslim, is this possible? 1, 1, 0, 1, 1, 0. Is this possible? Remember, 1, 1, 0 family, we have 1, 1, 0, minus 1, 1, 0, 1, minus 1, 0. In that case, this is possible. They all belong to 1, 1, 0 direction family. Then, okay, next page. So this is a table for typical room temperature, typical piezoresistance coefficients for N silicon, P silicon, P silicon, N silicon, pi 1, 1, pi 1, 2, pi 4, 4. Remember, we have unit 10 to minus 11 per Pascal. So this is the number, and this is the unit. Okay, previous. Now use table 18.1. And we know the direction, 110 direction. Then use those equations, previous. Use the equations next to calculate. For p-type, we get PL, pi L pi t. For n-type, we can get pi L pi t. Please remember the unit is 10 to minus 11 per Pascal. Okay, please write out your calculation. Okay, camera off. So now you have finished this calculation. Next page. Then, Amin, could you read this?
P-type long resistor have a larger sensitivity, and phi 1 and phi L and phi T have opposite size and almost equal magnitude.
See, if we can choose from p-type or n-type, pi L and pi L, for delta R divided by R equal to pi L sigma L plus pi T sigma T. If sigma L is the dominant one, sigma L is much larger than sigma T, then we should choose p-type polysilicon because it has higher delta R value. But delta R is important for sensor applications. But another thing is pi L pi T for p-type, magnitude almost the same, but the sign different. In the pressure sensor, later we are going to introduce this property is important. Pi L pi T, magnitude the same, opposite sign. But later we will discuss this later. Okay, next page. Next. So for U18 MEMS, we have polysilicon. Polysilicon is a piezoresistor. So we have N plus poly, P plus poly, and HR poly for us to select from. Non-solid poly. Solid poly means we add metal into the polysilicon to increase the conductivity but decrease the resistivity. So we prefer we do not add metal to the poly. So non-solid poly means no metal added to the polysilicon. So for non-solid poly, we have N plus, P plus, and HR poly. And for N plus poly, P plus poly, we need to use this equation. The perimeters belong to N plus poly. Perimeters belong to P plus poly. For HR poly, we need to use this equation. And current density is limited to 0.5 ampere per micrometer. So when you apply voltage, you need to remember, you need to calculate current density because the maximum value allowed is 0.5 milliamp per micrometer. Higher than this value, you are going to burn your poly resistor. Then your device won't work. So for mechanical engineer, your brain should put current and voltage into your brain. Otherwise, whatever you do for your layout, in the end, it will not work. Just a waste of time and money. Next. Now, this is the pressure sensor. If you feel sleepy, just wash your face, jog one round, then come back to office. Or watch some video to make you excited. Okay? So you can show them the video you watched to make you excited. So which video were you watching? You don't remember? Okay, for this pressure sensor, we have a diaphragm, a membrane on top. So this is the top view. This is the cross-sectional view. So we have a cavity. We have gas inside. So we have pressure to apply stress to the diaphragm, to the membrane, very thin membrane. We put 4 piezoresistors, R1, R2, R3, R4, on top of the diaphragm. These 4 piezoresistors will form a Wheatstone bridge. Wheatstone bridge, R, for voltage output. Then the resistors are along 110 direction. So you have calculated the pi L and pi T values for piezoresistors on 100 wafer along 110 directions. Then for stress and strain relations, we have some beautiful equations for you to enjoy. For a coordinate system, X, Y, and Z. So suppose on the wafer surface, we assign X and Y direction. And the Z direction is normal to the wafer. Then usually the diaphragm is very thin. It's just like a paper, very thin paper. For a very thin paper, like this one, it's very thin. So it cannot support Z direction force. So it means there's no Z stress. For the plate, for this one, very thick, so you apply force. So we will generate Z direction stress. But for a paper, like this one, if I put a large force, it cannot support. It will just deform. So just use this example to tell you, for a very thin diaphragm, in the Z direction, almost no stress. So we can forget about Z direction stress. And for X and Y coordinate, we have some beautiful equations for you to enjoy. Epsilon X equal to can you create one PPT page, the new, okay, then full view. Okay, then we have a large area for me to write the equations. Okay, for coordinate system, X and Y, then epsilon X is the strain in X direction equal to 1 over E sigma X minus nu sigma Y. and strain y equal to 1 minus e sigma y minus nu sigma x. Before we continue, let me define. If we have a y, we fix one end, we apply force at the other end. Then, see, if you apply a force to this wire, it will become longer. So we can calculate original length at 0, the new length at prime. So the elongation divided by original length equal to epsilon x, strain in x direction. And also for a wire, if you make it longer, its thickness will become smaller. So in the thickness direction, original thickness is T0. The new thickness, a smaller one, is T prime. So let's say Y is the thickness direction. For new thickness minus original thickness divided by original thickness is the strain in Y direction. And there's a relation between epsilon x and epsilon y. In this case, epsilon y equal to minus nu times epsilon x. So nu here, we call this Poisson ratio. So if you have a wire, you make it longer, you create epsilon x, but at the same time, the thickness is going to become smaller. So there's a ratio between sigma x, epsilon x, and epsilon y. The ratio is Poisson ratio nu. Okay, so now you know what is Poisson ratio nu. And this is Young's modulus. E is Young's modulus. The slope of the stress-strain relation. Okay, so this is the basic equation we will use in this pressure sensor case. Okay, now go back to that page. Okay, this one. Now, for this plate, see, we have the membrane, and here is fixed. So, edge here is fixed, edge here is fixed, this edge fixed, this edge fixed. Those four edges are fixed to the wafer. Then along those four edges, there's no strain because they are fixed. They cannot become longer, they cannot become shorter. So there's no change in length, means there's no change. There's no strain at all. So if there's no strain, say parallel to edge. So this is the edge. So this edge, parallel to this edge, there's no strain. So remember, say strain along the one direction equal to 1 over E sigma 1 minus nu sigma 2. So this is 1, this is 2. But epsilon 1 is 0, means sigma 1 must be equal to nu sigma 2. Because epsilon 1 is 0, and E is not 0, so everything inside this parenthesis must be 0. So that's why sigma 1 must be equal to nu sigma 2. Muslim, do you agree? Do you agree with me? Kumail, do you agree with me? Ethan, do you agree with me?
Yes.
Yes. Kumail, can you teach Kumail?
What is the value of E 0? 1 by epsilon naught.
Can you teach Kumail? Do you understand? Agan? Can you teach Agan? Do you understand? So, Muslim, you can listen. Do you understand? Then, please. Volume on, camera on. Let's begin. So, see, parallel to H, the stress, sigma 1 parallel to this H, equal to nu sigma 2 normal to this H. Okay, so for the 4 H's, we have this H1, 2, 3, 4. We have this relation. Okay, now the change in R1, delta R1 divided by R1 equal to pi L sigma in one direction plus pi t nu sigma normal to A, because this one is sigma t, but sigma t equal to nu sigma L. So you can take one in this direction, or one. Okay, one here, R1. So delta R1 divided by R1 equal to pi L. So this is, and parallel normal to H. So this is, if this is one direction, and we do, so this is a little bit misleading. So let's just follow this. For one, we have sigma, we have epsilon. Epsilon in this direction is 0. So this one is, say, 1 prime equal to 1 over E sigma 1 prime minus nu sigma 1 prime 2. Sorry, 1. So this is, if this is 1 prime direction, so this is 1 direction. Along 1 prime direction, strain is 0. But strain in 1 prime direction equal to 1 over E sigma 1 prime stress along this direction minus nu stress perpendicular to this direction. So because sigma 1 prime, epsilon 1 prime is 0, so we can say sigma 1 prime equal to nu sigma 1. So now let's come back to delta R1 divided by R1 equal to pi L. So L is the R direction. Then the sigma in R direction is sigma 1 prime. So because we say this is 1 prime, so sigma 1 prime plus pi t, and this is perpendicular to the R1 direction, pi t sigma t, pi t sigma t, this is sigma 1. Pi t sigma t, this is 1 prime. pi L sigma L, sigma L. So this is, sorry, this is one direction, this is one prime direction. This is one direction, this is one prime direction. Because epsilon 1 prime is 0, so we can get sigma 1 prime equal to sigma 1 prime equal to nu sigma 1. Okay, so remember this is one direction, this is one prime direction. So now let's come back to delta R1 divided by R1 equal to pi L, sigma L. Now sigma L is sigma 1 plus pi t. Pi t is sigma 1 prime. Okay, now but sigma 1 prime equal to nu sigma 1. So we can replace sigma 1 prime by nu sigma 1. So that's why we can write delta R1 divided by R1 equal to pi L sigma 1 prime, sigma 1 prime plus nu pi t nu sigma 1 prime. Pi L sigma 1 prime plus pi t sigma 1 prime, but sigma 1 prime equal to nu sigma 1. Okay, so for one direction, normal to edge is 1 prime. So this is sigma 1 prime. Pi t nu sigma. What the hell? Epsilon 1 prime equal to 1 over E sigma 1 prime minus nu sigma 1. So sigma 1 prime equal to nu sigma 1. Okay, so we can write. So this is sigma 1 prime. So this is sigma 1. Am I right? And why I write normal to edge? Normal to edge is sigma. So this is one direction.
Yes, one direction, one prime. So you can put right here to there.
So they are. It makes sense.
Yeah, it makes sense, but your definition is different.
Just a little bit complicated. Okay, I'm happy the TA got it. So so now nu value in 110 direction. In 110 direction, the nu has a value 0.064. So nu has a value 0.064. So for p-type, delta R1 divided by R1 equal to this value. Okay, so please calculate. And if you have question, ask Hugh to help you out. Okay, please start this calculation. Let me clean all this. It's too confusing. Yeah. Okay, previous. Yes. Yeah, calculate this one. Use pi L. Pi L in. You have calculated pi L in 110 direction. So you have pi L value. You have nu value. You have pi L pi t. And you have nu. And this is sigma L. This is nu sigma L. So sigma L here. And plug in pi L pi t and nu. You can get this value. So this is the edge. This is normal to edge. Normal to edge. maybe this is simple. You can just follow the equation to get this one. Parallel to H, strain 0. So sigma parallel to H equal to nu sigma normal to H. Camera off. Now, let's focus on R2. In R2 direction, delta R2 divided by R2, we have pi L, sigma L plus pi T sigma T. So this is sigma. Sigma L now is along the H direction. And sigma T is normal to H direction. But now in this direction, there's no strain. So in this direction, no strain, which means in this direction, there's no strain. Then sigma along this direction along minus nu sigma in this direction should 0 because epsilon, this is along, epsilon along equals 0. So which means sigma in this direction equal to nu sigma in this direction. But this direction is the length direction of R2. So the stress here, this one equal to nu sigma normal. So nu sigma normal. Nu sigma normal equal to, so this one alone equal to nu sigma normal. So that's why this is nu sigma normal plus pi T sigma normal. So we can calculate delta R2 divided by R2 equal to this one. So now calculate this one before we end this case today. Calculate this one, please. Okay, camera off.